I want to tell you about one of the most peculiar and profound truths I encountered in my life's work with atoms. They absolutely refuse to have their picture taken. Now, I don't mean this in some whimsical or poetic sense. I mean it quite literally. The atom refuses to be photographed, to be visualized, to be captured in the kind of definite, sharp image that we expect from the macroscopic world. And the reason for this refusal reveals something extraordinary about the nature of reality itself. When I was young, growing up in Copenhagen in the late 19th century, the atom was still a matter of considerable debate. Some scientists doubted atoms existed at all. They seemed like a useful fiction for chemistry, but not necessarily real entities. By the time I entered physics, this was beginning to change. Einstein's work on Brownian motion, Perron's experiments, the growing body of evidence from chemistry and thermodynamics, all of this was making the atomic hypothesis increasingly difficult to deny. But even as we became confident that atoms existed, we had no clear picture of what they looked like. J. Thomson had discovered the electron in 1897, showing that atoms contained these tiny, negatively charged particles. Thomson proposed what became known as the plum pudding model, electrons embedded in a sphere of positive charge, like raisins in a pudding. It was a reasonable guess, but it was wrong. The revolution came from Ernest Rutherford's laboratory in Manchester, where I had the great fortune to work starting in 1912. Rutherford and his students, particularly Hans Geiger and Ernest Marsden, had performed an experiment that shook the foundations of atomic physics. They fired alpha particles, helium nuclei, at a thin sheet of gold foil and observed how they scattered. Most of the particles passed straight through, which was expected. But some of them, a tiny fraction, bounced back at large angles, some nearly straight back toward the source. Rutherford was astounded. He later said it was as if you had fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. The only explanation was that the atom was mostly empty space, with almost all its mass concentrated in a tiny, dense nucleus at the center. The electrons must be orbiting this nucleus at relatively large distances, like planets around the Sun. This was a beautiful picture, vivid and mechanical. We could imagine it clearly. But there was an immediate and devastating problem. This atom could not exist. According to Maxwell's electromagnetic theory, which had been confirmed in countless experiments, an accelerating charged particle radiates energy. An electron orbiting a nucleus is constantly accelerating, changing direction, even if its speed remains constant. Therefore, it should be constantly radiating energy, losing speed, and spiraling into the nucleus in a tiny fraction of a second. Every atom should collapse almost instantly. And yet, here we are, made of atoms that have persisted for billions of years. I spent weeks wrestling with this paradox. I walked the streets of Manchester, I sat in my rooms, I discussed it with colleagues. The classical physics we had inherited from Newton and Maxwell was magnificent, but it was giving us an impossible answer. Something had to give. And what had to give, I eventually realized, was our insistence on a classical picture of the atom. The key insight came from Max Planck's work on blackbody radiation and Einstein's explanation of the photoelectric effect. Both had shown that energy in electromagnetic radiation comes in discrete packets, quanta. The energy of a quantum is proportional to the frequency of the light, with Planck's constant as the proportionality factor. This was already strange enough, but I saw that this quantization had to extend into the structure of the atom itself. In 1913, I published my model. I proposed that electrons could only occupy certain specific orbits around the nucleus, orbits characterized by having angular momentum that was an integer multiple of Planck's constant divided by 2 pi. In these special orbits, and only in these orbits, the electron would not radiate energy, despite classical physics saying it should. An electron could jump from one allowed orbit to another, emitting or absorbing a quantum of light with energy equal to the difference between the two orbital energies, but it could not exist between these orbits. This model worked beautifully for hydrogen. It predicted the spectral lines, the specific colors of light that hydrogen emits, with remarkable precision. It explained why atoms were stable. It gave us a framework for understanding atomic structure. But even as I celebrated this success, I knew something profound was missing. I had imposed these quantization rules by hand, forcing them onto the classical framework. I had not derived them from deeper principles. I had created what my colleague Wolfgang Pauli later called a quantum patchwork. And crucially, this model still relied on a picture. I was asking people to imagine electrons in definite orbits, following definite paths. But this picture, I would come to understand, was misleading. The atom refuses to conform to such visualizations, and the reason goes to the heart of quantum mechanics. The full revolution came in the mid-1920s with the development of quantum mechanics proper. Werner Heisenberg, working with me in Copenhagen, developed matrix mechanics. Erwin Schrödinger, working independently in Zurich, developed wave mechanics. These two formulations looked completely different mathematically, but they were proven to be equivalent. And both of them abandoned the attempt to visualize atomic processes in classical terms. Heisenberg's uncertainty principle, which he discovered in 1927, made explicit what was already implicit in the formalism. You cannot simultaneously know both the position and the momentum of a particle with arbitrary precision. The more precisely you determine one, the less precisely you can know the other. This is not a limitation of measurement technique. This is not about experimental error or the disturbance caused by our instruments, though that plays a role. This is a fundamental property of nature itself. Let me make this concrete. Suppose you want to take a picture of an electron in an atom. To take a picture, you need to bounce light off the electron. Light comes in quanta, photons. When a photon strikes an electron, it transfers momentum to it. To get a sharp picture, to pinpoint exactly where the electron is, you need light with a short wavelength, which means high energy, which means the photon will disturb the electron significantly, changing its momentum dramatically. If you use gentler light with a longer wavelength to minimize the disturbance, your picture becomes blurry. You cannot determine the position precisely. This is why the atom refuses a picture. The very act of trying to observe where an electron is changes what you are trying to observe. And it is not just that we are clumsy observers. Even if we could design a perfect experiment, nature herself sets a limit. The product of the uncertainty in position and the uncertainty in momentum must be at least on the order of Planck's constant. This is not negotiable. But it goes deeper than this. In quantum mechanics, an electron in an atom does not have a definite position until we measure it. Before measurement, it exists in what we call a superposition of all possible positions, described by a wave function. This wave function gives us the probability of finding the electron at any particular location if we choose to measure its position. But the electron is not secretly at some definite location that we simply don't know. It genuinely does not possess a definite position until we measure it. This is extraordinarily difficult to accept. Our intuition, built from everyday experience with macroscopic objects, tells us that things have definite properties whether we look at them or not. A chair is in a definite location in a room whether I am observing it or not. But electrons are not tiny chairs. They do not obey the same rules. The quantum world operates according to different principles, and we must abandon our classical intuitions when we descend to the atomic scale. I remember long discussions with Albert Einstein about this. Einstein had contributed enormously to the development of quantum theory. His explanation of the photoelectric effect, his work on specific heats, his insights into the wave-particle duality of light. But he could not accept what quantum mechanics was telling us about the nature of reality. He believed that particles must have definite properties independent of observation, that there must be some deeper level of description where everything is determined, even if hidden from us. His most famous objection was encapsulated in the phrase, "God does not play dice with the universe." He meant that nature, at its deepest level, must be deterministic, not probabilistic. The probabilistic predictions of quantum mechanics must be a sign of our incomplete knowledge, not a fundamental feature of reality itself. I responded, perhaps a bit cheekily, "Einstein, stop telling God what to do." But the disagreement was profound and philosophical, not flippant. Einstein devised numerous thought experiments to try to show that quantum mechanics was incomplete or inconsistent. At the Solvay conferences in Brussels, he and I would engage in intense debates. He would present an ingenious setup that seemed to violate the uncertainty principle or show that quantum mechanics gave contradictory predictions. I would spend hours, sometimes all day, analyzing his argument, and by evening I would show him where it failed, where quantum mechanics remained consistent. The most famous of these challenges came later, in 1935, when Einstein, working with Boris Podolsky and Nathan Rosen, published what became known as the EPR paradox. They considered two particles that had interacted and then separated by a large distance. According to quantum mechanics, these particles become entangled. The quantum state of the two-particle system cannot be factored into independent states for each particle. A measurement on one particle instantaneously affects the state of the other, regardless of the distance between them. Einstein argued that this was absurd. Either quantum mechanics allowed faster-than-light influences, which violated relativity, or the particles must have had definite properties all along, determined at the moment of their interaction, and quantum mechanics was simply an incomplete description. He called the apparent instantaneous influence, Spukhaft-Fernwirkung, spooky action at a distance, and he was convinced this revealed the flaw in quantum mechanics. But the flaw was not in quantum mechanics. The flaw was in insisting that particles must have definite properties independent of measurement. The EPR argument assumes what we call local realism, that objects have definite properties whether we observe them or not, and that influences cannot propagate faster than light. Quantum mechanics denies the first assumption. Properties emerge through the act of measurement, they do not exist independently beforehand. Now you might ask, how can we be sure? Perhaps Einstein was right that there are hidden variables determining everything, and quantum mechanics is indeed incomplete. This question remained open for decades. But in the 1960s, long after my death, John Bell proved a remarkable theorem. He showed that any theory based on local hidden variables must satisfy certain mathematical inequalities. These Bell inequalities can be tested experimentally. And when the experiments were performed, starting in the 1970s and continuing with increasing precision ever since, nature violates Bell's inequalities. Quantum mechanics is correct. There are no hidden variables preserving our classical intuitions. This brings me to what I called complementarity, perhaps my most important contribution to understanding quantum mechanics. Complementarity is the recognition that a complete description of quantum phenomena requires mutually exclusive experimental arrangements. You can set up an experiment to observe the particle-like properties of an electron, or you can set up an experiment to observe its wave-like properties, but you cannot observe both simultaneously. The properties you observe depend on how you choose to observe. This is why the atom refuses a picture. A picture presumes that we can visualize all properties simultaneously. That an electron is here with this momentum, following this trajectory. But these properties are complementary. To measure position precisely, you must use an experimental setup that makes momentum indeterminate. To measure momentum precisely, you must sacrifice knowledge of position. You cannot have both in a single snapshot. Let me describe a famous experiment that illustrates this perfectly, the double-slit experiment. Imagine firing electrons one at a time at a barrier with two narrow slits. Behind the barrier is a screen that lights up where electrons hit it. If electrons were simply particles, we would expect them to pass through one slit or the other and form two bands on the screen, one behind each slit. But that is not what happens. Instead, an interference pattern forms, multiple bands of light and dark, exactly what we would expect if electrons were waves passing through both slits and interfering with themselves. Each individual electron somehow goes through both slits at once and interferes with itself. This is the wave aspect of the electron's nature. Now, suppose we try to determine which slit each electron actually goes through. We can place detectors at each slit to observe the electrons. When we do this, the interference pattern disappears. We see two bands, one behind each slit, exactly what we would expect for particles. By observing which slit the electron goes through, by trying to see the particle aspect, we destroy the wave behavior. The two descriptions, wave and particle, are complementary. Both are necessary for a complete understanding, but they cannot be accessed simultaneously. This is not sleight of hand. This is not a clever illusion. This is nature telling us something profound. Quantum objects are neither waves nor particles in the classical sense. They are something fundamentally different, something that exhibits wave-like or particle-like properties depending on how we choose to interact with them, how we set up our experiments. And this is why, when we try to visualize an electron in an atom, to take its picture, to say where it is and what it is doing, the atom refuses. The electron does not have a trajectory. It does not follow a definite path. Before we measure it, it exists in a superposition of possibilities, described by a wave function that extends throughout the space around the nucleus. The wave function gives us probabilities, not certainties. And when we measure the electron's position, we collapse this wave function, forcing it to manifest in one particular location. But in doing so, we lose information about other complementary properties. I developed what I called the correspondence principle to help bridge the gap between quantum and classical physics. The correspondence principle states that in the limit of large quantum numbers, large orbits, high energies, the predictions of quantum mechanics must approach those of classical physics. The quantum world and the classical world must somehow connect. And they do. When systems become large enough, when they involve enough particles or enough quanta, quantum effects average out and classical behavior emerges. This is why we do not see interference patterns when we walk through doorways, even though quantum mechanics applies to us as much as to electrons. Our wave function has an extraordinarily short wavelength because of our large mass. The quantum effects are there, but they are utterly negligible at our scale. The uncertainty in our position is so small compared to our size that it is completely undetectable. But for electrons in atoms, quantum effects dominate. The wavelength associated with an electron is comparable to the size of the atom. You cannot separate the electron from its wave nature. And this wave nature is what makes visualization impossible in the classical sense. Instead of pictures, we must use mathematics. The Schrödinger equation describes how the wave function of a quantum system evolves over time. For an electron in a hydrogen atom, we can solve this equation exactly. The solutions are called atomic orbitals, and they tell us the probability distribution for finding the electron at various locations around the nucleus. These orbitals have beautiful mathematical properties. They are characterized by quantum numbers that specify energy, angular momentum, and the orientation of that angular momentum in space. The lowest energy orbital, called the 1s orbital, is spherically symmetric. The electron is equally likely to be found at any angle from the nucleus, though most likely to be found close to it. Higher energy orbitals have more complex shapes, dumbbell shapes, cloverleaf shapes, intricate patterns of nodes where the probability is 0. We sometimes draw pictures of these orbitals, showing surfaces that enclose regions where the electron is likely to be found. These pictures can be useful, but we must be careful not to take them too literally. They are not pictures of the electron itself. They are pictures of probability distributions. And at any given moment, the electron does not have a definite position, it exists in a superposition of all the positions consistent with its orbital. Moreover, when an atom contains multiple electrons, they cannot be described independently. The electrons are entangled with each other. The state of the atom is not just a collection of individual electronic states but a single, unified quantum state of the entire system. This is why chemistry is so complex, why the periodic table has the structure it does, why atoms bond in the ways they do. It all emerges from the quantum mechanical interactions of electrons that refuse to be localized, that spread out in probability clouds, that influence each other in subtle and profound ways. The Pauli exclusion principle, discovered by Wolfgang Pauli, adds another layer to this story. It states that no two electrons in an atom can occupy exactly the same quantum state. This is not a consequence of the Schrödinger equation directly but comes from a deeper property. Electrons are fermions, particles with half-integer spin, and fermions obey what we call Fermi-Dirac statistics. This exclusion principle is why atoms have the sizes they do, why matter is stable, why different elements have different chemical properties. If electrons were distinguishable classical particles, we could put as many of them as we wanted in the lowest energy orbital. Atoms would collapse to incredibly small sizes. All elements would behave similarly. Chemistry as we know it would not exist. But electrons are indistinguishable quantum particles that obey the exclusion principle, so they must occupy different orbitals, filling up the energy levels in a characteristic pattern. This is the foundation of chemistry, of materials science, of biology, of everything built from atoms. All of this complexity, all of this richness, emerges from the atom's refusal to be pictured, from the wave nature of matter, from the uncertainty principle, from complementarity, from the fundamentally probabilistic nature of quantum mechanics. If atoms behaved classically, if we could visualize them the way we visualize macroscopic objects, the world would be unrecognizable, probably incapable of supporting the complexity necessary for life. I want to address a common misconception. Sometimes people hear about the uncertainty principle and think it means we are uncertain, that we simply do not know what is happening. But that is not correct. The uncertainty is not in our knowledge but in nature itself. Before we measure an electron's position, it does not have a definite position. It is not hiding somewhere, waiting for us to find it. It genuinely exists in a superposition of positions. This is perhaps the most difficult aspect of quantum mechanics to accept. It seems to violate our basic intuitions about reality. We want to believe that things have definite properties independent of observation, that reality exists, out there, in a determinate state whether we look at it or not. But quantum mechanics tells us this is not how nature works, at least not at the atomic scale. The measurement problem, as it is called, remains one of the deepest puzzles in quantum mechanics. When exactly does the wave function collapse from a superposition to a definite state? When we observe it, certainly. But what counts as observation? Does it require a conscious observer? Or will any measuring device do? Different interpretations of quantum mechanics give different answers to these questions. In what became known as the Copenhagen interpretation, which I helped develop, measurement occurs when a quantum system interacts with a classical measuring apparatus. The apparatus records a definite result, and the wave function collapses accordingly. But where exactly is the boundary between the quantum system and the classical apparatus? This boundary is somewhat fuzzy, somewhat arbitrary, and this bothered many physicists. Other interpretations have been proposed. Hugh Everett suggested that wave functions never collapse, that all possible outcomes occur, branching into separate universes. This many worlds interpretation avoids the measurement problem but at the cost of an enormous proliferation of universes. David Bohm developed a pilot wave theory with hidden variables that reproduce quantum predictions while maintaining determinism, but at the cost of non-locality, instantaneous influences across space. Various decoherence-based approaches explain how quantum systems appear classical when they interact with their environment, though they do not fully solve the measurement problem. These debates continue, and that is healthy. Science thrives on questioning, on probing our assumptions, on seeking deeper understanding. But regardless of interpretation, the experimental facts remain. The atom refuses to be pictured. The uncertainty principle holds. Complementarity is real. Quantum mechanics makes predictions of astonishing precision, confirmed in countless experiments over nearly a century. And these quantum effects are not merely academic curiosities. They are the foundation of modern technology. Lasers depend on the quantum nature of light and atomic energy levels. Transistors and integrated circuits depend on quantum mechanics of electrons and semiconductors. Magnetic resonance imaging uses the quantum property of nuclear spin. Atomic clocks, GPS systems, solar cells, LEDs, all of these depend on our understanding of quantum phenomena. We have learned to harness the atom's quantum nature, even though we cannot picture it classically. More recently, we are developing quantum technologies that exploit uniquely quantum properties like superposition and entanglement. Quantum computers promise to solve certain problems exponentially faster than classical computers. Quantum cryptography offers theoretically unbreakable security. Quantum sensors achieve precision impossible with classical devices. All of this builds on accepting, not fighting, the atom's refusal to conform to classical visualization. When I look back on my life's work, I feel a deep satisfaction mixed with a profound sense of wonder. We set out to understand the atom, to see how nature works at the smallest scales. What we found was stranger and more beautiful than anyone had imagined. We found that visualization itself is a classical concept that does not apply to the quantum world. We found that observation and reality are inseparable. We found that nature is fundamentally probabilistic, not deterministic. We found limits to what can be known, not from lack of effort or ingenuity, but from the structure of physical law itself. The atom refuses a picture, and in that refusal, it teaches us something profound about the nature of reality, about the limits of visualization and classical thinking, about the role of observation in bringing forth the properties we measure. This is not a failure of science but one of its greatest triumphs. We have learned to describe, to predict, to understand atomic phenomena with extraordinary precision, even without being able to visualize them in the comfortable, classical way. This requires a kind of intellectual humility and flexibility. We must be willing to abandon our intuitions when they conflict with careful observation and rigorous reasoning. We must be willing to work with mathematical abstractions even when they do not correspond to visualizable pictures. We must accept that nature is under no obligation to conform to our expectations or our evolved habits of thought. And yet, within these constraints, within this strange quantum world, there is extraordinary beauty. The mathematical structure of quantum mechanics is elegant and powerful. The patterns of atomic spectra, the periodic table of elements, the richness of chemical bonding, all of this emerges from the wave nature of matter, from the exclusion principle, from the quantization of energy and angular momentum. The atom's refusal to be pictured is not a barrier to understanding but a gateway to deeper understanding, if we have the courage to follow where nature leads. This is what I learned from a lifetime of studying atoms, that reality is more subtle, more strange, more wonderful than our pictures of it. That the map is not the territory, that our visualizations are tools, not truths. That mathematics can take us further than imagination alone. And that in accepting the atom's refusal to be pictured, we gain something far more valuable than any picture, genuine understanding of how nature truly works.